Hello, math fans. I'm Dr. Andy Lovelace, a longtime professor, 20 years at the University of Washington. If you've been watching my other videos, you know that I'm occasionally releasing just side videos for my own enjoyment, things that I've found interesting over the years. This particular video is mostly for me. I went to the University of Puget Sound. I had some great instructors. In particular, I remember Ron Vaninkyvort, who taught me calculus and many other courses. And really, in large part, the reason I continued in math was because of him. And I'm sure I never told him, and I probably was never appreciative. I had several other great instructors, Robert Beezer, John Rigsecker. Apologies, I may not even be saying your name right. I feel so bad. I was so inattentive as a student. Let's see, who else was I going to mention? And then we'll get to talking about the definition of the derivative, but I'm mostly going to use this as an opportunity. Brian Smith taught me abstract algebra. I learned a lot there. And it really has informed me as an instructor. I teach large classes, about 400 students a quarter, and I've kind of gotten worn down by the things I've had to teach, and I want to share some of the fun things, and that's what this is about. If any of these people see this video, I'd love to have pictures of all of you, get updates on how everyone's doing. I'm terribly out of touch, but I want to give some credit. Mostly, I have stolen from all of you, and I don't even know who I'm stealing from. Now, Hey Jude, I'm almost certain I stole from Professor Vaninkyvort. Monkey Faces, I'm pretty sure I stole from my wife's one of my wife's high school teachers. Wholesale cancellation, that might have been a Beezer thing. The fact that I always say, hello, calculus fans, I think I stole that from a computer science professor, but I'm blanking on the name. So if you can help me with any of these things in the comments, I would love to know all these things I say, where they came from. And to illustrate what I'm talking about, I'm going to talk about the definition of the derivative. So the definition of the derivative is this. This is not really a math talk, but we want to know the slope of the tangent. This is where calculus starts at a given point, and we do that by finding the slope of the secant. We do this rise over run thing. Change in y over change in x. And then we figure out what happens as this h gets smaller, as this distance gets smaller. So I'll show a couple of visuals, and then I'll come back and we'll talk about what in the world am I talking about with Hey Jude, Monkey Faces, and wholesale cancellation. So here's a quick visual. This is the function, and this is one thing that I didn't have in the day when I was a student. But here's the function y equals x squared. Here's a couple, I'll leave those points there. And there's this, what we call secant line. As h gets closer and closer to 0, those points get closer together, the slope is going to be more and more like a tangent line. Boom, there we are. Oh, it went away. So we talk about the tangent slope. So if you've taken calculus, you've played this game before. It's a foundational idea. But let's play the game, and let's have some fun along the way. So let's say you have this function x squared, and for some reason you want to simplify what happens when you do, let's play the game. And calculus students have trouble with this, the fact that there's an x here, and sometimes I plug in, this is my own thing, I think, but it doesn't matter that this is x, it could be w, it could be z. I always like to plug in broccoli, so I don't think I stole that from anyone. Broccoli plus h minus f of broccoli over h. It's just a location. It's a box. Okay, so we're going to plug in x plus h. So we're going to do x plus h squared. And if any of my former professors catch this video, they're going to be like, really? You're going to go into the details? And I do it a much better way. And I have no doubt you do it a better way. Anyways, this is what it is. This limit as h goes to 0 of this expression. It would sure be nice to simplify it, but if you plug in 0, you get 0 over 0, you get an error. So as I tell my students, we are on a mission to make this h go away and hopefully cancel. And that mission was typically involves just simplifying. And if we can, then we'll have the slope of the tangent. And I'll finish this video with a little bit of a justification about tangents. The quick justification is we'd really like to find these bumps. I think that's my own thing I made up. But if you want to find the bumps of a graph, it sure would be nice to know when the slope is 0. And when in doubt in calculus, take the derivative and set it equal to 0. But we're going to expand this out. So there's several bits of algebra. One of my current colleagues says calculus is where you learn your algebra. All math teachers complain about the algebra of their students, but the truth is calculus puts your feet to the fire, and you have to actually show you know what you're doing. Okay, so first, monkey faces. Students always say FOIL, which I think means first, outside, inside, last. But my wife's high school teacher said monkey faces. Now, she was trying to remember, and she was unsure of which high school teacher it was. There was this teacher, Calkins, but he taught her siblings and sang the quadratic formula, which I do that. But I think it's a different instructor, and she was unsure. But you can see the eyebrows and the nose and the mouth. It's a monkey face. I say this many times a quarter. We're going to monkey face it out. It doesn't help students in any way, probably. But it reminds them that they have to expand this, and it's kind of fun to look at that monkey face. So what happens? You get this x squared. That's the eyebrow. One eyebrow, if I can raise it. And then you have xh. That's the mouth. And then you have hx. That's the nose. And then you have h times h. That's h squared. And that's what this was right here. And then we have minus x squared, all divided by h. And I tell my students, if you're doing it right, you remember your goal, that this h is going to go away. You're hoping it does. You're hoping it simplifies in a way that you can actually say something about this as h gets smaller and smaller. You should also expect, so I like to give what I call mileposts along the way, you should expect that this will cancel. You should expect it should cancel because there's an f of x here, and there's an x also being plugged into f with some adjustments. So you should look for cancellation. If whatever comes out of this doesn't cancel, you should be worried. And usually that means you've done some problem with expanding. So anyways, those two things cancel. Hooray! So that's a success. And I had a professor that would say wholesale cancellation. So there's a lot of cancellation that happens here. This is not a full example of wholesale cancellation. That might be a Beezer thing. I don't know who that was. But anyways, these are things I say. But really what I say is we're going to take something that's messy, which is this or this, and we're going to clean it up. And when we do, we sing, "Hey, Jude." We're going to take a sad song and make it better. That's what we're singing. Now, I apologize for singing. It takes special significance to me because I have a niece who I absolutely love who is named Jude. And so I have to stop myself from saying, "Hey, Jude," every time I see her because I love that song. But we're going to take a sad song and make it better. Now, the sad thing for me is that when I make that reference, very few students get it anymore. Yet I continue. So, Professor Vinicky-Vort, I am trying to make it live on. We're going to take a sad song and make it better. So anyways, the next step, I often say to my students, are you going to divide this by h or this by h? You got to divide one of them. So we cancel. You got to divide both. It's distribution, or you can factor. So we talk about this in two ways. If you're a person who loves factoring, and I laugh a lot, as you can see, I have 20 years of teaching 1,200 students a year has made me lose my mind slightly, but I'm trying to just show you some of the things I enjoy about doing math. This is the limit. The definition of derivative is not something I really play around with very much, but what I enjoy is these little quirks that I've learned over the years that I think help students remember. So we finally did it. Success. That h went away. You plug h equals 0, and this is a big thing. Sometimes students say, what is calculus? The derivative of x squared is 2x. That's it. That's all calculus is. That might be a little more. The other way you can think about it is distributing 2x h over h I just had a discussion with my Calculus 2 class. A student was asking me, why don't we divide the 2 and the x and the h by h? They really wanted me to do this. And I went, I'm sure glad that arithmetic doesn't work that way. You just divide, you don't distribute when all it is multiplication and division. Maybe that's a thing for another video. But these are the little things that cause people trouble. Anyways, the limit as h goes to 0 of 2x plus h. And then you get 2x. Okay, so the slope is 2x. That's where calculus usually starts. And we have these monkey faces, this Hey Jude, this wholesale cancellation, these milestones to help us along the way. And I find that math is easier when you have a little bit of a story to go with it. So anyways, that's this thing. Let's get rid of that now and talk about slope. So the slope of the tangent line, let's make it a true tangent line. The slope of the tangent line 1 is 2. The slope of the tangent line at 2 is 3. Now, just going further, I've already, this video is too long already, but an interesting thing is if you take x cubed, things look a little worse. You're doing x plus h cubed, and my undergrad instructors don't know this, but in grad school, I spent a lot of time with Pascal's triangle and binomial coefficients and studying large prime numbers. So if you don't, I think that'll be many videos in the future. Pascal's triangle is this. If you've never seen it, we actually used it right here when we did monkey facing. But if I'd used Pascal's triangle, I wouldn't have been able to say monkey face. They're these coefficients. So the coefficients here, it goes like this. X squared h, x h squared, and then there's an h cubed, and the coefficients are 1, 3, 3, 1. Pascal's triangle has a lot of interesting things about it. You get the next number by adding the previous 2. Sorry, I don't know why I labeled that one. Minus x cubed over h. And ultimately, we're going to take the limit as h goes to 0 of this, but we get to do it again. Wholesale cancellation. We're going to take a sad song and make it better. Wholesale cancellation. Hey Jude, let's take that sad song and make it better. Which one of the h's do we divide out? Well, we divide 1 out of each one. 3xh plus. It's always small things put together in math. Occasionally it's something bigger, but doesn't require extreme talent. I've made it this far. I don't have extreme talent. When you plug in 0, you get this. So the derivative of x to the third, or the slope of the tangent line, is 3x squared. We took a sad song, we make it better, we plugged in, got to a place where we could plug in h equals 0. If you do x to the fourth, you get this term right here that looks like 4x to the third h. And that's where all these things come from. You get x to the fourth. I encourage you to try to do that. You get 4x to the third as the derivative. And then we build. And calculus usually spends several weeks building rules. How you can do sums. Here's x cubed. How you can do differences. There's the tangent lines. In the end, we then say, well, what if we have a function that has bumps? Where are the bumps? Where are the peaks and the valleys? Well, those are places where the slope is 0. And so this all ends with an extremely powerful tool. The formula itself tells you the height. The derivative tells you the slope. And if you want to know where the function is 0, then setting the function equal to 0 is great. But if you want to know where the bumps are, you want to set the slope equal to 0. So here's this function, x cubed minus 2x. Let's go back here. Here we go. Here's this function. X cubed minus 2x. We take the derivative. It turns out there's this thing called the sum and coefficient rule. I say that the sum and coefficients come along for the ride, and then you use the derivative rules. 3x squared and the derivative of x is 1. Again, this video is not about this, but then you can think of this as the height, and you can think about this as the slope. And when you encounter a question like where are the bumps, Apologies to my former professors that my graphs are so bad that I'm being a little careless here, but these videos are meant for fun. Set this equal to 0, you get 3x squared minus 2. I would always stop with my students and say, what is that? Is that a hook? Is that a paper clip that's been bent out of shape? No, it's supposed to be a 3. When is that equal to 0? Well, that would be when 3x squared is 2. That would be when x squared is 2/3. And that would be when x is plus or minus. And I think it's impressive how quickly we can do that. We can find the bumps. It's plus or minus the square root of 2/3 with almost no effort. So when people are first seeing this, they're like, oh, this is a lot of effort, these definitions. But in the end, it's making our life easier. We're not trying to make it harder. I think students don't make it to the place where your life gets easier sometimes, and because of that, they're like, why are we learning this? Maybe you still think that anyways. But my goal is to not have to deal with that question as much anymore. I think it's interesting in and of itself. So I know where that bump is. It's when that slope is square root of 3/2, and then this one back here. Ooh, way too fast. 0 and 3, let's say. Let's animate it. Oh no, that's too fast. Here we go. Let's go back here. Way back here. Oh, now it's too slow. Then the video went on for many hours. Anyways, we can find those bumps. So I'm going to finish with that. I may tweak this video again, but my intent is, if anyone knows the professors at University of Puget Sound, I'd love to get an update on how everyone is doing. I apologize, I did not make it to Professor Beezer's retirement party. I have 3 kids, I'm extremely busy, and so many students. But I would love to give credit where credit is due. If anyone knows where... So hey Jude, thank you, Professor Finicky-Vort, for getting me interested in math and telling me that it's something I could continue doing, because I didn't think about it as a possibility. Monkey faces, I think, is something connected with my wife. Wholesale cancellation, I think, is a Beezer thing. Professor Carrick was a computer science professor that would say, hey, computer fans or something. So I appreciate all these sayings. They gave me stories to build on, and they made math fun, and I hope I am continuing tradition with my own students. All right, thank you.